Hi, everyone. I'm Mark Westlake. Welcome to our presentations this afternoon. You're going to hear from four amazing high school invent teams and one collegiate prize-winning team. So thanks for joining us this afternoon. My name is Mark Westlake. I'm a 2008 invent team moderator, and I'm a current Lemelson MIT master teacher. After teaching physics for 28 years, I'm now the director of the St. Thomas Academy Innovation Center. And I could not be more excited about being a host for this room and introducing you to these amazing students and their inventions. A couple of housekeeping things. If you would like to watch us closed caption, that is an option. Live captioning is available, and you can turn that on with one of the buttons either at the bottom or the top of your screen, depending on what you're looking at. And I'd like to remind people that they can send their questions in via the question and answer pane, the Q&A pane at the bottom of their page. And then I will either answer it or I'll have the teams answer it via the chat box. So welcome again. And we don't want to take any more time away from the teams. So I'll introduce Benilde St. Margaret's Invent Team. They are located in St. Louis Park, Minnesota. Their moderator is Anne Schneemann Doherty, who does an amazing job over there with their engineering program. They've invented a device to extend the reaching capabilities for people using wheelchairs. So Benilde St. Margaret, it's all yours.
Hello, everyone. I am Annie Gollenville. I'm a member of the Benilde St. Margaret's Invent Team. I'm a senior this year. And for people unfamiliar with our school, we are a private Catholic preparatory high school in St. Louis Park, Minnesota. Our team is made up of a group of seniors and 2 sophomores, and most of us have been working together for the past 3 years. We first heard of Invent Teams the beginning of our junior year. We applied for the grant, were not successful our first time, and then tried again our senior year and were able to get it. So I would like to introduce you to our team, starting with our 2 teachers, Miss Doherty and Mr. Wixer. And then our students include Sophia DePaula, Jillian Petty, Gabby Pasco, Danny Mergen, Ava Denowell, Jillian Brown, Gabe Carlson, and Julia Domino.
Hi, I'm Danny Mergen, and I'm also a senior. Our team has been working with Courage Kenny, which is a rehabilitation institute in Golden Valley, Minnesota. Courage Kenny's goal is to help everyone they treat achieve their highest level of independence, health, and wellness. To help some of their patients, we are making a robotic arm that will extend from a wheelchair to help people that have limited mobility with everyday tasks like pressing an elevator button. This arm will be compact, so it doesn't get in the way of anything. It will be fast, and it won't waste any time. It will be accurate so that the arm is easy to use. We are working to make the control system for the arm as simple as possible so that anyone can control it.
Hi, I'm Ava Denowell. We got the idea to build the robotic arm from Matt White, who is an occupational therapist at Courage Kenny. Matt informed us about a common complaint that a lot of people have with restricted motion. Traveling from point A to point B is seemingly easy on an electric wheelchair, but as soon as the operator needs to reach an elevator button that is outside of their range of motion, they need help. This issue restricts their freedom and might even make them feel helpless on their own. To have their own independence and not rely on other people for help is a big improvement in the life of a wheelchair user. So our invention would achieve those needs.
My name is Jillian Brown. Courage Kenny has served thousands of people since their founding in 1942. Right now, they don't have any patients who use powered wheelchairs with robotic or mechanical arms because it's prohibitively expensive. During our initial patent search, we discovered similar robotic arm designs for powered wheelchairs, but they're very bulky and incredibly expensive. We have partnered with a Minneapolis-based patent attorney who has given us multiple resources to help us learn more about existing patents that are similar to ours, but we believe that we will be able to clearly differentiate our arm from the existing patented arms. Our arm is an affordable, slim, and user-friendly version that retracts smoothly from the arm of the chair. Our arm can't do multiple tasks yet, but it is a reliable and simple tool that can handle this specific action reasonably.
Hi, my name is Gabby Pasco. And so we have experimented with the arm after attaching it to a wheelchair, and we've had many test runs with an elevator. Most of the data we collected was just comments we got from the trial runs. So our claim was that we could make a cheaper alternative to the mobility accessories on wheelchairs in comparison to the average sale price. We have completed this by making a product that is around $250. Another goal that we had when starting to build this was to make the arm compact, and we have achieved this by making the armrest under the wheelchair so it doesn't get in the way when the user is driving around normally.
Hi, I'm Sophia, and I'm going to tell you a little bit about our arm for the wheelchair. So this is our second prototype, and we plan to continue to advance it as time goes on. The arm moves horizontally out, and then it can rotate vertically. And then we have a video to show you about how it works.
Hi, this is Sophia.
And I'm Jillian, and we're sophomores at Benilde St. Margaret.
Yes, we're going to show you how our arm for the wheelchair works. So basically, there are 3 buttons. Sorry, this one came undone. There's 3 buttons. Red one stops the arm. Green one goes counterclockwise. Blue one goes clockwise. So if I were to click it, it would go out. I can stop it right there. There's a potentiometer to rotate the arm up and down. When it's on the wheelchair, it will be a lot stronger than Jillian's arm, of course. But I can also put it back in, and then on the wheelchair, it will be resting fully unextended underneath the armrest, so it won't be in the way of anything. So, yeah, thank you.
Although we are happy with how far we have come, we know that our invention can continue to be improved. Next year, students are going to continue to work on our idea and perfect it so that we can start to give it to more people to use. So I'm going to pass it off to Sophia, who will lead the team next year. She's a sophomore, but she is going to continue this for the next 2 years, most likely.
Yeah, hi, it's Sophia again. We have many improvements we want to make for this arm. First off, we are going to get a bunch of feedback from wheelchair users throughout the summer. We are going to give them the arm, and they're going to give us a bunch of feedback, telling us what they think that we should do better. As an inventor, it's really important to understand what your client is needing. So that's very important to us. With what we know right now, we are going to make the arm longer from 14 inches to 18 inches. So they have more accessibility with pressing the elevator button. We are also going to make the buttons bigger for people who have less fine motor skills. And with that, we are going to continue to improve the arm for a couple years to go. We are very excited, and we hope that we can help a bunch of people with this later.
We have several people we would like to thank for helping us make this possible. First of all, we would like to thank Matt White and Courage Kenny for their continued support throughout this time. We'd also like to thank Benilde St. Margaret's and the engineering department for the resources they have provided us. And then we would like to thank Lemelson MIT for giving us this amazing opportunity and resources to get us this far. We wouldn't have been able to do any of this without these people, and we're very thankful. And that wraps it up. So if anyone has any questions, they can put that in the Q&A and we will answer them.
Well, I have a quick question for you. Could you talk about some of your failures along the way? Some things that you might have tried that didn't work?
So yeah, we have actually had a bunch of different prototypes and things. This is one of them actually. So this one works like a kind of, it had a servo motor and it pulls a string to extend it and things like that. We thought this wasn't very reliable because sometimes the servo wouldn't work or the string would get attached to something, and it was also very bulky and wouldn't be able to like get through doors normally. So we have adapted to these other ideas. And we also had a bunch of problems with just getting it exactly right and different problems with coding and stuff. So yeah.
That's great. Thank you. If there are no other questions, we will move on to our next speaker. Thank you, Benilde St. Margaret, and thanks for taking the time to do your presentation. You guys did a great job. Next, I'd like to introduce our student prize winners. MIT every year, Lemelson MIT program offers $10,000 grants to college students, both undergrad and graduate students, to invent things in different categories. This year in the Move It category, Songwon An and Maya Birkenperker from Harvard University invented an add-on technology that enables wheelchairs to become fully autonomous. Maya, I've watched the video. It's absolutely stunning the way that wheelchair drives around. And obviously this is a technology that really could benefit not just the individual user, but hospitals everywhere. So I'll turn this over to you, Maya Birkenperker.
All right, first just to check, can everyone see my screen? Wonderful,
Yes.
Okay. So hello, my name is Maya Birkenperker, and I am a physics and computer science student at Harvard. Although today I am calling in from near Toronto, and I'm going to present on behalf of the Adventist robotics team. So our society is aging. Many of us have elderly friends and relatives whose mobility has decreased as they've become older. And power wheelchairs are often used to help increase mobility for those with neuromuscular and age-related conditions. However, the joystick interfaces, as well as the alternative input devices like sip and puff switches and eye tracking software, can be very difficult for these people to use. And our startup's autonomous technology, we hope, will change that. So at Adventist, we've created a fully autonomous hardware and software stack that can be installed onto any existing power wheelchair to make it autonomous. Our software and hardware are robust with redundancy and fail-safe detection systems. And it's capable of operating in large scale and chaotic environments without the use of any external beacons or infrastructure, which means that you can use it pretty much anywhere. So as was mentioned earlier, there are a couple of different use cases that we're currently focusing on. So the first and I think most obvious one is the personal at-home use case. And the second one is the hospital use case, but I'll focus on personal first. So if you're a wheelchair user, how do you actually use this technology? Well, when the system is first installed on a wheelchair, the caretaker will turn it on and then push it. So push the wheelchair around the environment, like the user's house or their place of work, enabling the onboard computer to create a map of that environment. They can then mark off specific locations on the map, like the bathroom or the kitchen, using a graphical user interface. And then after that initial setup, all the user has to do is turn the wheelchair on, and it will automatically localize itself within that map, and then take the user to their desired destination entirely autonomously. The software that we wrote for the at-home use case also has a second package called an assistive mode package. So the process that I just described needs to happen in a pre-mapped environment. But people can find themselves in all sorts of places. And in our user interviews, we found that there are a few tasks that are very, very common, but also very challenging to power wheelchair users. And so we created an assistive mode package that enables users to travel through doorways, down corridors, and then also park at desks or tables. These are all things that require very fine joystick control, but we can take care of it with our autonomous software. The second use case is hospital portering, and this is one that may not be familiar to a lot of people, but I think it's a very important one. So at major hospitals, inpatients, regardless of whether or not they're injured, are pushed in wheelchairs from their rooms to their appointments. And this is typically done by porters, wheelchair porters, whose job it is to push people in wheelchairs. The unfortunate thing is that the delays associated with the portering process result in substantial inefficiencies. So we did a white paper with Toronto General Hospital, and we found that in their imaging department alone, the delays associated with portering added up over the course of a year to about $6 million of equipment idle time and thousands of appointments that should be happening that were missed because of late patient arrivals. And in the context of COVID-19, this close proximity contact associated with portering increases the potential for disease transmission. And this is something that we've seen time and time again throughout this pandemic. So of course, our autonomous system can help by both reducing the amount of close proximity contact between patients and porters and making that process safer, as well as increasing efficiencies, allowing hospitals to see more patients per year. So we've talked a little bit about what the applications are and what it does, but let's talk a little bit about how it works. The technology uses a theoretical concept that was developed decades ago. So it's something called simultaneous localization and mapping. But until recently, it was practically impossible to safely implement. So our retrofit kit consists of a robust array of sensors that are placed around the wheelchair. And those are used by an onboard computer to continuously create a map of the environment that the wheelchair is in, as well as locate itself within that map with astonishing accuracy. And with extensive testing, including thousands of hours of both physical in-person testing, as well as simulation in Amazon Web Services, as well as our unique integration of hardware-based fail-safe mechanisms, we were able to develop the first autonomous system capable of transporting individuals safely. So zooming back out of the weeds for a couple of seconds, at Adventus, we've developed a safe, fully autonomous wheelchair system to make the lives of the elderly and those with neuromuscular conditions better. That's all I had. I'm happy to take any questions.
For your wheelchair, the sensors that you're using, is it LiDAR, is it sonar, is it infrared?
Yeah, that's such a good question. And this is something that really we spent the majority of our time on. As you're aware, there are plenty of different kinds of sensors that you can put on autonomous systems. And all of them have different accuracies and different error profiles, and maybe most importantly for any consumer system, different costs. And so trying to navigate that was something that was incredibly difficult for us because, you know, you can always purchase a $20,000 LiDAR and put it on your system and it'll have great accuracy, but no one's going to be able to afford that. So the answer is that we use a combination of many different kinds of sensors. So we have RGB cameras and we do image processing on that. We do have LiDAR, although very inexpensive LiDAR, as well as odometers, accelerometers, all sorts of things. And really the magic happens with the sensor fusion that's done on the onboard computer that's able to combine data from all of those sensors in a way that doesn't make the error worse, but actually makes it a lot better.
Do you see the next step moving from pre-mapped environments to a place where a user could actually go anywhere and the automation would still work?
So, you know, part of the conceptual difficulty there is that if you're a computer, you sort of need to know where you where you can go. And so, you know, there are ways of getting around that. If you can, instead of being in a pre-mapped environment, if you can provide, you know, maybe a schematic map to the computer, then that's certainly a direction that one can go in. And also something that I should clarify is, you know, if you have, for example, in the context of a hospital, if you're getting 20 of these wheelchairs, you certainly don't need to create the map for each one individually, right? You can just create the map for one and then share that map with all of the rest of the other systems. And so, you know, I don't think there's a situation in which you could ever have something going where it's just the environment is completely unknown, because even in that case, as a human, I wouldn't really know where to go. But there are certainly workarounds to this mapping requirement.
Maya, this is absolutely amazing. Can you just give us a little bit of your background and where you plan to be in the next couple of years?
Yeah, absolutely. So as I mentioned, I'm from Canada. I've been here since the pandemic started, but this project was something that I think in retrospect was really quite a long time coming. I grew up around wheelchairs because my grandfather was actually an occupational and physiotherapist. And so a big part of the work that he did was actually doing wheelchair fit tests for a variety of people. And so growing up, I was very familiar with the challenges that face wheelchair users. And at the same time, especially about 10 years ago, I mean, autonomous technologies were just taking off all over the media. And I thought, well, hey, wouldn't it be cool to put these two things together? And I got really fortunate. I found a lab at the University of Toronto where they were working on the earliest stages of a project like this. And the professor in charge was just the kindest, most generous and patient mentor I've had the pleasure of working with. So I think really all the stars just aligned there. In terms of where we're going, of course, the direction is in trying to get this technology out there so that people can use it. And there are always so many challenges associated with commercializing, especially hardware-based technology. I'm sure you've heard all about the incredible valuations of software startups from Silicon Valley, but hardware is fundamentally a little different. There are costs associated with manufacturing, and it takes time to put together production lines and those kinds of things. But nevertheless, that's what I'm focused on.
And we have one question from a viewer, and they want to know: is the space on the wheelchair where is there a space on the wheelchair where the passenger can store personal items, or does the technology limit the room that they have?
So the answer is not really. The sensors are all fairly small, and they're placed sort of all around the wheelchair in places where you wouldn't normally store things anyway. So we don't. We first of all, we retrofit the wheelchairs, so we're not designing a wheelchair from scratch or anything like that. So if there is already onboard storage space, our system wouldn't affect that.
And then finally, the last question. I have two daughters, and I know that we have an almost all girls team on here from Benilde and an all girls team from the Archer School. As a young woman in STEM, have you found that it's been easy to access everything that you wanted to?
I think I've been really fortunate. I wouldn't say that there were any challenges associated with accessing anything because of my gender or anything like that. I mean, what I would say is that sometimes it can be a little bit isolating. I think things are getting better, but nevertheless, in a lot of my classes, there just aren't that many women. And so it really makes me very pleased to see the amount of female representation on the teams here today. I think it's really important that we all support each other as much as we can. So if I can ever be of help, I'm always happy to. Oh, I think you're on mute. I think you still are.
I'll remind people as we move along that we can always submit questions via the chat box. Maya, thank you so much for being part of the program and for congratulations on winning the Move It Prize from the Lemelson MIT program. We'll move on to our next high school team, which is the Archer School for Girls. And they're taught by Mike Carter, a friend of mine in Los Angeles, California. And they've worked on a system to detect embers and actuate a roof sprinkler system. So I will turn this over to the Archer School for Girls.
Hi, I'll start. Okay. Hi, my name is Gabby Ayala. I am the head of administration for this Invent team. I am a graduated senior and have been on the Archer Invention team for the past 4 years. I have had the pleasure of leading this team for the past 2 years, and I'm excited and proud to pass on this leadership role to Michaela Winehouse, a rising senior on the team, who will become the administrative lead of this Invent team this fall. Now I'd like to start our presentation by telling you a bit about our team. Our team currently consists of 32 students, 21 high schoolers and 11 middle school students, who are divided up into 7 committees. administration, app design, budget, CAD, engineering, programming and motion, and communications. Our records show that over the past year, we have had over 50 students on the team, 6 through 12, some dropping due to Archer COVID conflicts. Our school, the Archer School for Girls, is located in Los Angeles, California. Our invention, Hydra, is very connected to our community's needs, and you'll see why in the following slides. This team came together with the recruitment of the Archer Invention Club. Recruitment is done through promo videos and live presentations to the school. Often, students are involved on the invent team, invite friends to join, whether it is a sports teammate or a classmate. Autumn Walker, my good friend, will tell you all of
Hi, my name is Autumn Walker. I'm a rising 7th grader here at Archer, and I'm going to tell you about how I joined Invent Team. The day I heard about Invent Team, I was reading in my room when I heard my sister on an Invent Team call. So I ventured over to see what it was, and I was hooked. They talked about code, designs, and some things that I hadn't even heard of, and all in such a fun and easy environment. After the call, my sister asked if I'd join Invent Team. I sprinted out of her room and sent an email straight to Gabby to see if I could join. And sure enough, I was an official member the next day. I found that the reasons I joined Invent Team resonate with the purpose of our team and club, which is to encourage fellow classmates and friends to have fun learning, exploring, and creating together. Now I'll hand it over to Sabrina Walker, who will talk about the need for Hydra.
Hi, my name is Sabrina Walker, and I am a rising 10th grader at Archer. Many residents in California are faced with wildfires. In the summer of 2019, massive fires spread across the state, burning over 2 million acres and threatening the lives and homes of thousands. Our school had to evacuate twice in 4 years, and it was closed for more than 2 weeks when the fires threatened our homes of our friends and family. Research has found that 90% of homes are lost due to embers that are blown from the original wildfire and land on rooftops, therefore setting the home ablaze.
Hi, my name is Destiny. I'm a rising senior. With our invention, we hope that homeowners along with firefighters benefit from the use of it. Our device, an automatic sprinkler system that uses infrared cameras to detect and extinguish approaching embers and any resulting of hotspots, is the solution to the massive property destruction caused by wildfires. And our ultimate goal is to provide homeowners with a protective measure to guard against these deadly wildfires.
Hi, my name is Eliza Childs, and I'm a rising junior and a member of the engineering committee. Our invention helps houses and buildings from burning down and thus decreasing the spread of wildfires. The threat of wildfires has increased at an unprecedented rate as environments become more prone to wildfires due to climate change. Hydra's infrared targeted system extinguishes embers and eliminates the spread of wildfires, not only saving homes and properties, but also those who stay behind attempting to protect their homes. Now I'm going to hand it over to Michaela, who will speak about the uniqueness of Hydra.
Hi, my name is Michaela and I'm a rising senior. Through our research of patent and market research, we have found that there are several devices that help protect homes from wildfires, but none deploy automatically or incorporate infrared cameras with object tracking. The Roof Saver sprinkler on the left and the Ember S-Guard on the right both mount onto roofs and adjust to different roof pitches. They incorporate several long-range sprinkler heads to cover a roof with continuous water spray. The wildfire protection system on the left is a rotating sprinkler that can be installed on a roof to extinguish nearby materials on fire. These devices must be manually controlled, whereas Hydra will activate automatically. Our device also has more advanced fire detection systems than prior existing sprinklers. The WaveGuard system on the right uses a basic infrared sensor to detect fire and turns on sprinklers that spray water and fire retardant through each system, though each system is configured uniquely to suit a property. Additionally, the large space automatic infrared target water sprinkler fire extinguishing system uses an infrared sensor to detect indoor fires. However, neither include our device's ability to pinpoint and extinguish moving embers. Our device does not infringe on any existing patents and includes unique extensions to prior art. In particular, no other invention has our remote control app and data sharing features. Also, current roof sprinkler systems made to protect buildings must be manually turned on and are left constantly running, which diverts water from firefighters. In contrast, our device activates only when necessary. Now I will hand it over to Karen, who will speak about Hydra's design.
Hi, my name is Karen Garcia, and I am a rising junior and the leader of the CAD, or the Computer Aided Design Committee. When thinking about our design criteria, we prioritized Hydra's movement, using water in an efficient way, and integrating the electronic, mechanical, and design systems. We based our design off of a strobe light, which moves 180 degrees vertically and horizontally. Using the strobe light as a foundation, we could then add electronic and mechanical components. Here, there is an acrylic base with rounded edges that holds plumbing parts that connect to 4 stationary nozzles. These stationary nozzles allow for Hydra to extinguish any embers that surround Hydra, providing a second level of protection for embers that are not extinguished from the targeted nozzle. There's also another rectangular acrylic piece that is above the rectangular base that will holds electronic components. We chose to implement this tier system so that if there is a leak from plumbing parts at the bottom, water will not enter the electronic parts because of their elevated stance. Finally, the base and arms of the spotlight frame are propped above the second tier that holds the nozzle, and it also holds its corresponding outer shell. Next, Chloe will explain how the nozzle uses information from the infrared cameras to track an ember.
Hi, I'm Chloe Hayden, and I'm a rising sophomore and a member of the motion programming team. Our device's tracking works with the help of blobs. A blob is a collection of pixels that are the same color and have the same heat signature. The computer takes in the blobs and is able to track the center of them. The infrared camera detects these yellow-colored heat blobs, and the device moves to eradicate them, which in a real-life scenario will be the embers. We know that the motion tracking works because it has successfully tracked heat signatures as shown in the videos. We will continue to improve our tracking in cooperation with the Los Angeles Fire Department. Now, Maya will go over how our app functions.
I got it. Hi, my name is Maya Alvarez, and I'm the co-lead of the App Design and Programming Committee. Within the app, users are able to interact with Hydra with real-time status checks on all of Hydra's main parts, as well as controlling the amount of time Hydra is shut off in the scenario that you are using a controlled fire. Additionally, users can personalize the app by including their available water sources and zip code that determines the best fire news sources and gives Hydra access to a backup water supply during a wildfire. Overall, the user experience with the Hydra app is meant to be simple and efficient, so users can calmly navigate during a time of crisis.
Hi, my name is Nina Solomon. I'm a rising senior of the Communications and Outreach Committee, and I'll be talking about Hydra's impact on Archer and the greater community. So as our team has worked to create our device, we have been sharing our process and efforts with both our school community and those beyond it. The start of our project began with a school-wide survey searching for an issue that many people care about. This survey found that due to many students being displaced and forced to evacuate from their homes because of wildfires, this issue was one that struck deeply in the community. Since then, we have shared our project with Archer families, showcased our device at the middle school science fair, and hosted many information sessions to encourage students to join our team. We also have been featured on Spectrum News and soon the LA Daily News, as well as meeting with local firefighters to improve our device and connect with our community.
Hi, my name is Lily and I'm a rising junior. I'm a member of the budget committee and I'm going to present the finances and total amount of money spent for the creation of Hydra. So far, we've spent about $6,200 out of $6,700, about 92% of our budget. Out of 6 committees, funds have been spent primarily on the Programming Motion Committee, and electronic component orders have made up 35% of our funds spent. Additionally, the Mechanical Engineering Committee has ordered mechanical components that have made up 21.5% of our budget. Wearable promotional materials make up 18%, and there are also other categories that make up our funds spent, such as testing equipment, food, and lab safety supplies. Additionally, our estimated cost for Hydra is $5,000. This price factors in the electrical, mechanical, and design components of our device and other factors that contribute to the making of Hydra. We want Hydra to be as affordable and accessible as possible. And we hope the cost of Hydra will decrease as we improve our design, production increases, and we receive input from our community. Now I'll pass it off to Alejandra to talk about our next steps.
Hi, my name is Alejandra. I am a rising 10th grader and I am on the programming motion team. Our next steps are to keep working on and refining the device. We will also continue to do on-campus testing to correct any errors.
Hi, my name is Danny and I'm a rising junior. Next year, our team is also planning on filing a patent for Hydra and making our invention a protected design.
Our team is lucky enough to have met with both the Los Angeles Fire Department, including Chief Terrazas, and the LA Clean Tech Incubator. Through these meetings, we made plans to test Hydra safely with LAFD and sustainably with LA Clean Tech Incubator. The legitimacy of our testing is so important to us, and we are so excited to work with these groups in the future.
Hi, my name is Addie Myers, and I'm a rising freshman. I would like to thank the Los Angeles Fire Department for meeting with us to speak about Hydra improvements and hearing their stories of battling fires firsthand. In addition, thank you to Captain Philip Ward of the Pasadena Fire Department and David Solis of the Malibu Fire Department for your overwhelming support and guidance throughout the year. I would also like to thank Glenn Meyerowitz, a UCLA computer and electrical engineer graduate student, for all the time and guidance he has given our engineering committee over the semester.
Hi, my name is Hannah Cho. I'm a rising 7th grader, and I'd like to thank the Archer administration and Board of Trustees for supporting the team throughout the duration of the project.
Hello, my name is Lola Thomas, and I'm a rising 8th grader on the app design committee. I would also like to thank our mentors, Mr. Carter and Miss Finney, for giving us constructive feedback and making sure we had all the resources necessary to bring our device to life.
Hello, my name is Jessica Guo, and I'm a rising 8th grader. Our entire team would also like to give a huge thank you to Tony, Mark, Aaron, and everyone with Lemelson, MIT, and Buzz Engine. And congratulations, Invent teams.
Thank you all for coming to our presentation. We hope you enjoyed it and have a great summer. We will now move to the Q&A session. Please feel free to drop any questions in the chat.
We do have a couple of questions. One of our watchers wants to know, how does your device distinguish between the extra heat caused by direct sunlight versus heat from an ember?
Thank you so much for that question. I will have Amanda Green, our lead programmer, answer that for us.
Hello, I lead the programming motion committee. We're working on the object tracking, obviously, and there are many different types of blobs, obviously, and we can track we can filter which blobs we detect based on circularity and how big they are and how fast they're moving. So the sun is a big circle and it's moving really slowly. So we can take those parameters and write them in our code so that they will not detect that blob and not confuse it with fire.
Okay, I have to tell you that this is an amazing invention. I can't even turn on my sprinkler at home without managing to get wet. Congratulations. I am wondering if one of the possible uses of this would be to keep rabbits out of my strawberry garden. Could I set it up so that it senses the heat from the rabbit and then gives it a little squirt to make it go away?
That's actually really funny that you asked that, Mark. Earlier this year, we had a 6th grader ask us the same version of a question. What happens if there's a squirrel on the roof? Is it going to shoot the squirrel if it's because of its heat signature? And then we ended up getting that same question from a firefighter a few weeks after. But I'm sure that if you register the heat signature using Amanda's method of a certain scale, whether it's like a white for flames and then red for heat signatures, you can tell the difference. So I think we could do that.
Really well done. Thank you very much, Archer School for Girls. We'll move on to our next team. That's the Bram High School team. Bram is in Bram, Minnesota. Their moderator is Luke Becker. Luke runs a lot of different programs and works with NASA on a couple of different projects. And so it makes sense that his team would choose a project that was space related. The Bram High School Invent team chose to design a system to wash clothing in microgravity, thereby reducing the waste in space. So Bram?
Hi, I am Ben White from Bram High School. I am in 9th grade, and we designed a microgravity washing machine.
Hi, I'm Allison Morell. I'm in 10th grade, and I worked on the communications and the sustainability portion of this project.
Hello, I'm Jaden. I am a 12th grader, and I worked on the research and the building part of the project.
Hi, I'm Lizzie. I'm in 9th grade, and I helped with the finance stuff.
Hi, I'm Addie. I'm currently in 8th grade, and I help with finance as well as being one of the team leads.
Hello, I'm Ava. I'm in 8th grade, and I helped out with the communications portion of the project. Usefulness. Astronauts on the International Space Station wear their clothes for around 2 weeks before they are deemed unfit and given to a resupply ship, which takes them away and provides them with more clothing. After that happens, it is discarded in the Earth's atmosphere where it burns up, and that wastes resources and ends up being pretty expensive for no reason. It's an unrealistic solution for longer missions into space because that's a lot of going back and forth, and that's not possible.
Alrighty, so our machine solves lots of these problems by basically just allowing astronauts to wash their clothes instead of disposing of them. So this, reduces waste on the ISS. Before they're taken away to be burnt up in the atmosphere, they kind of just sit around the ISS, which causes an unpleasant odor both while they're wearing them and while they're waiting around to get rid of them. So
Hey team, can Ben turn his camera on for us?
There. Is it working now?
Yes, it worked great.
sorry about that. And so this also reduces the waste that goes into the atmosphere. We don't want to cause any unpleasant situations by just throwing him out into space. And then, like Ava said, sending the clothes up to the ISS is pretty expensive. And so this allows for more resources, more important resources to take up that space that the clothes would be on the resupply ships. So.
Concept to reality. In the pictures shown left to right show how our machine has evolved from being just like a bag and then went to a Mountain Dew bottle, and now it is the result of the far right. So we've come a really long ways and learned from a lot of the differences we've made.
With the uniqueness of our machine, nobody has created a device that's intended for microgravity. So with our machine, we can't use any
detergent because if you use detergent on the ISS, all of the water is connected. And so it could affect the drinking water of all of the astronauts that are on the ISS. And you can only use 500 milliliters of water. That's about the size of a regular water bottle. There can be little to no movement on the ISS because if there is movement, it can affect some of the experiments that are going on the ISS. The machine also must be completely sealed. If it's not completely sealed, there will be problems with water leaking and getting into the controls of the ISS. And if that happens, things can go very wrong.
All right, and reduce to practice. This in the photo shown is our clear model. We used this to make sure that everything was working how we wanted it to, and then we could see if there were any errors and make it so that our machine was the best it possibly could be. We did this multiple times through tests so that we could see ways that we could improve it and make the machine better.
So for our size requirements for the washing machine was a double locker on the ISS. But we found out that our machine is actually roughly the size of a single locker. So NASA sent us an actual single locker to make sure that we were able to fit it into the single locker. Having this take up less space is actually better and able to have more room.
Alrighty, so here we have a video of our clear model. The pistons, after all the controls and programming is done, the pistons moving up and down to draw water in and out, both air and water in and out, as well as create agitation. This was very important because in space, both water and air are very hard to control, especially together. So yeah, this was kind of, once we got everything put together and working.
So these are our test results. We used a workout shirt and it was returned to its original softness and all of the odor was eliminated. We used a new clean shirt and it pulled some of the dye out. But it was overall still pretty clean. It removes 50 to 60% of the water in the chamber. And it's able to wash pants that are similar to NASA's. Over the past month, we have met with patent lawyers and have been creating our application. As a team, we have been preparing for our trip to Houston and perfecting the machine before we go. Thank you for coming. If you have any questions, feel free to leave them in the chat.
Well done, Bram High School. I remember I had the opportunity to listen to Scott Kelly speak one time. And one of the things that he said is that nothing had prepared him for his visit back to the International Space Station for the smell that he encounters when they open that hatch in between the capsule and the International Space Station. So it's not good, I guess. So you're doing a good thing. You guys can turn off your shared screen, and we do have some questions for you.
Yeah.
So one of our listeners wants to know, would this work on Earth, or does it only work in a microgravity environment?
It does work on Earth, and that's one of the cool things is we can kind of repurpose it to help areas that might not have as much resources. You know, they don't have they don't have detergents, they don't have very much water, and they're would be able to still effectively wash their clothes on Earth and save those resources.
It is more sustainable to use on Earth because it only uses 500 milliliters of water, which is the size of one water bottle. Oh, sorry. It is the size of one water bottle, and it only runs on 12 volts. So we could use a 12-volt solar panel to power it.
So this is about the size of how much water it would use if this was full.
So can you give us some ideas about what the problems are with working with water in the International Space Station and in a microgravity environment?
So with working in space, air and water cannot be separated. So that's something that we've been trying to work on, as well as having limited amounts of water. We are trying to use as little as we can. And since all the water is connected, there can't be any like chemicals in it. So we're trying to not use chemicals.
And as we've seen from other, astronauts' videos of kind of life on space, water itself, especially since there isn't gravity there, obviously, it's very hard to control the movement of it. So
what are the next steps for this project?
We're trying to get a patent on it, and then as soon as we can get it to NASA.
And I heard that the engineers at Johnson Space Center had invited you guys to bring it down and show them in real life. That's pretty amazing.
Yeah.
That has to be something that's pretty exciting for you.
Yes,
absolutely.
Graham High School, thank you very much for working on this and for doing your presentation. We'll move on to our last school. This is the Landmark School located in Beverly, Massachusetts. Their teacher is Doug Walker, and they have a device that monitors near-shore ocean environmental variables. So Walker, Landmark School.
Hello, can you guys hear me?
It's great.
Perfect. So my name is Nicholas Guthrie, and I'm with the MIT Invent team. And to give you guys some background on what our project is, we prepared a short little video.
That knowledge is power, but to have knowledge, one needs data. At the Landmark Invent team, we're building a near-shore data buoy that will test a number of environmental indicators that are studied to understand the health of the ocean environment in Salem Sound, helping us better our understanding about the ocean right off our local shore. We plan to have a system that collects important environmental data that can be used to study and understand changes in the ocean environment. It is also Landmark's intention to lower the cost of collecting this data and to be able to share this with other students and schools that can use the information to learn more about our local ocean environment. Since data can be collected over months, students can learn that experiments are not just single day or single lab period events. Our system exhibits and reinforces the concept of long-term evaluation over a day, a week, and even seasonally. The data is also reported in real time, meaning one can get access to live data being recorded. This can be used in education and help environmental assessments of their marine ecosystems to further understand impacts of climate change. Seen in the video, the Landmark buoy floats from an anchor and collects data, both above and below the ocean surface. The flotation donut, in which the electronics are housed, remains dry. In response to requests from one of the end users, the team is currently working on adding an underwater hardware to measure the current speed. We hope this information helped you understand the intentions and hope for Landmark Invent team to help bring local environmental data and to educate as well as observe what is going on in their own backyards.
So I said in our the previous video, our mission statement is to create an affordable method to be able to collect and transmit environmental data from our nearshore ocean locations that then can be in turn used for education and environmental assessment of our ecosystem that is on our coast. This can then help us further understand the impacts that climate change has on our ocean. So our objectives were to provide qualitative data over a long-term period of time. So from month to month for seasons and for so that we are able to see the progression of change. Also to help students understand our local environment and the importance of long-term data collection. Additionally, we'd like to use this information to help forecast what may occur and make predictions on what will happen, and then also increase the interaction between various stakeholders. So our information is open source so that anyone is able to access the information and use this so that there can be a lot of collaboration between many groups of people. So our core mission comes a lot from our sensors. We will be measuring the surface wind speed, the pH of the water, the temperature of the air, the surface, and the depth of 3 meters. We'll be measuring water turbidity and along with barometric pressure. So our early brainstorming was on the concept of a flow chart and how it would work. We wanted it to be able to be in sleep mode while it wasn't working, then to be able to wake up when there was a set variable of a time. We could do this on the hour, every 15 minutes, every day, whatever interval we'd like. It would wake up, it would cycle and pull our GPS. It would then collect data from all our different temperature, from all our different sensors. It would then be able to save this data to an SD card. It would send it out as a text message. This text message, then information from the text message would automatically be imported into a graph. And then our buoy would return to sleep mode to have this occur again. So we went through our first iteration as seen on the left that had a almost donut-like thing to be able to hold our electronic components. Unfortunately, after being in the ocean for not many days, it got hit by a boat and it went offline because it sank to the bottom of the ocean. We did, however, learn a lot, and as seen on the right, we have already created a second iteration. So in this new iteration, we kept some things the same, like the way we are measuring wind speed, because in that short period of time while we got data, our system was online and it worked to provide data. We have also learned that the donut was not the most effective method, and we also added extra reflective tape. So existing methods are high cost. Our system is able to be inexpensive. They also, other systems also have a monthly expense to them. And some systems even have people send out on boats to collect this information. You're also forced to comply with what the company sells. And they have expensive maintenance and you only lease them and they're not actually yours. For our system, the only monthly cost is to pay for cellular data, which at its readiness is pretty inexpensive. It's also fully autonomous and is able to run completely by itself. It is fully customizable, so any set of sensors could be put on and then applied. And they're also very low maintenance, only having to be cycled in and out occasionally throughout a year. So our design was inspired off the winter spar. The spars are used to mark boat moorings during the winter months. They have an incredible durability, as seen time and time again, because they're able to last in New England weather, harsh storms, and they're able to stand up. So we have a PVC base with a closed cell foam for flotation. And then while in our testing, we also counterweight it to be able to make sure the correct placement of our sensors and whatnot is achieved. With that said, I'm going to pass it over to Matthew Favreau.
Hi, my name is Matt Favreau. I've done a lot of the technical and software stuff with the buoy. So our buoy, like Nick just explained, floats like 2 miles offshore and collects data, saves it to its SD card, and then uploads that through the cellular GSM module and sends that as an email, which then gets retrieved through a server and gets collated into a spreadsheet. And we're planning on collecting data all throughout the day, and then it gets sent out at the end of the day, and then you'll get the information. And if it doesn't get sent, you can go and find the data on the SD card that it should have recorded. There are other systems that are out there like ours. However, they're extremely expensive. They're like the satellites that they use for communication is way more expensive than the cellular data that is available. Cellular data is ubiquitous, and we've found that it's just it makes more logical sense to use that instead of satellites because it's right there, it's more or less expensive, and it makes data more available because the barrier for entry for getting this sort of technology is a lot cheaper. The circuitry has evolved over the time we've started to develop this. We've breadboarded it, and then we put it onto another sort of like perf board, and then we've made like tons of those, and then we modularized our design so you could like plop in a sensor if it doesn't like work or anything, or if it gets sunk down to the bottom of the ocean and something bad happens to the sensors, you can just like plop another one in. I don't know that would be a problem, but you could do that if you needed to. Also, our cell phone technology, like I talked about, it uses cellular data instead of satellites, and cell phones are a lot more inexpensive. And we've had some trouble with using the cellular data. The GSM modules that we use work on like a 2G network, which is not as like commonplace as other networks like 5G, 4G that are more out there now. So we're gonna figure out how to use those sort of frequencies instead of 2G and the lesser ones. So this is our data. It gets like automatically collated into the spreadsheet using like Google Sheets API, and the data gets sent from the email, read in the email, and then spat into the spreadsheet. This is like how the data would be like read. So what you're seeing printed out is like the GPS readings. And then that's like the temperature. It gets like 3 readings from the temperature of like different levels and the GPS. So if we lose it, we can go track and find it. Of course, if it's like at the bottom of the ocean, you cannot no longer grab that. It's just way too deep. I don't know why that'd be a problem, but yeah. This is next up is Caitlin Rattray.
Hi, thank you, Matt. Hello, my name is Caitlin Rattray. I'm a rising junior at Landmark High School. The final step of this project is to make a autonomous boat. Using all that we have learned from our data, we will switch from a static platform to a moving platform. This change in platform will enable us to constantly collect data and effortlessly change the location of data intake. The next steps the Landmark Invent team will take are continue to make the system more robust in the marine environment, install digital CT system, and start collecting useful and interesting data. Our benefactors are Salem Sound Coast Watch, Massachusetts Division of Fishermen's and Wildlife, Beverly Public School, and finally, Landmark High School. The cost of the current phase 2 boat is less than $1,000, which is good because this makes it more realistic. These are some photos of our team working on creating this buoy. The Landmark School Invent team would like to acknowledge Mr. Walker, Mr. Crossman, Mr. Bruto, and all of the administrative people, Salem Sound Coast Watch, Massachusetts, Manchester by the Sea Harbor, And finally, a massive thank you to Lemelson MIT program who made this possible. Thank you for being part of our presentation. Our website is linked below. Feel free to visit and see our progress. Any questions can be put in the chat bar. Thank you.
Thank you, Landmark School. There are a couple of questions. One is, how reliable is the cellular data during bad weather, and what's the range for the cellular data?
All right, I'll answer that question. The range is up to 2 miles, and once we start to use this 5G, it will definitely be more reliable than the 2G.
I'm going to have you guys turn off your screen sharing so people can see you.
Do this.
Hit the stop share.
Stop sharing the red.
Oh.
No.
There we go.
Wait, your video's on.
There you go.
Sorry for that.
Perfect. That's perfect. Can you tell us a story about when it got hit by a boat?
Oh yeah. I wasn't there for that. Who was there for that?
We know it was in the harbor.
Oh
Yeah,
well.
sailing team saw the damage.
It was in the harbor, and our sailing team was out one day practicing and found it, I guess. And we were able to retrieve the PVC piping and majority of it, besides the electronics that sunk to the bottom. But we were able to learn from that and come back better and build a better buoy.
We do have another question from Mr. Fusil, who is really has a deep understanding of what happens out in the ocean. He wants you to describe your anchoring system.
Yeah, so our anchoring system was, we had a chain connected to the bottom of the buoy, and the buoy was probably like 15 feet underwater, and it was probably an extra 3 feet with the anchor connected, and we kind of relied on our flotation of the buoy to help it stay stable through the water.
What is your goal for the data?
We want to be able to open source our data and share it to the surroundings with Salem Sound Coast Watch and Massachusetts Fishery Division, and be able to have them use it to learn more about the ocean life around us.
So working in a saltwater environment is really harsh on electronics. How are you able to encase those to protect them while they're out there, I mean, under storms and in the salt? And
Yeah, so we use what do you call it? Mineral oil. And we use mineral oil to cover it, and we also use special type of paint to cover the PVC piping so it doesn't have ocean life growing on it, like algae grow on it, to protect it. And we also used gaskets.
Yeah.
Gaskets, I guess. What was I thinking of? We use what was I thinking of? Flex seal. No. We did have Flex Seal to help with the tracks. God love the Flex Seal.
I love this next question. It says, how do you protect it from seagulls, seals, and other creatures?
We haven't really thought of that. We just, well, yeah.
The anemometer spins, and it kind of makes seagulls not want to go near it. So
There's also not a whole lot of space for them to land on it.
yeah, we purposely designed it to have minimal space for things to land on it, so they wouldn't do that.
That's great. Landmark School, thank you very much for your presentation and for your willingness to answer questions. That actually concludes our teams today. If you want to learn more about Invent Teams and about the other schools that have gotten Invent Team grants, you can always find that by looking at the Lemelson MIT website. If you type in Invent Teams, you'll find it in the search window. And I think that we probably have it on the last slide here. So again, thank you for joining us today. Teams, I'll remind you that the design challenge kickoff starts at 2:30 Eastern time, so 12:30 for the Minnesota schools, and I suppose that's 10:30 for our friends out at the Archer School for Girls. So again, thank you, and we appreciate all the work that you guys did and your amazing inventions.